So somewhere out there in the world right now, there's a metal cabinet,
Right.
and it's basically the size of a standard refrigerator.
Nice.
But it's drawing enough electricity to power an entire city block.
Yeah, a single cabinet. It's wild.
It is, and I mean, if you were to walk up to this cabinet and just say, sever its water supply, the silicon chips inside wouldn't just overheat and safely shut down. They would literally melt themselves into slag in like a matter of seconds.
Oh, absolutely. Total physical destruction.
Right. And I bring this up because when you, as a user, interact with an AI or an LM, it feels entirely weightless. You just type a prompt, and a response kind of magically materializes out of the ether.
It feels like it's just software floating in the cloud.
Exactly.
Yeah.
But the physical reality making that invisible magic possible is, well, it's the most power-dense, thermodynamically extreme engineering humanity has ever deployed.
It really is.
And today, we actually have the blueprints for one of those systems. We're doing a deep dive into the Supermicro AI SuperCluster user guide.
Oh, yeah. Specifically, release 3.1.0 from April 2026.
Right, which is basically the operating manual for a turnkey generative AI data center. Okay, let's unpack this. Because looking at this manual really shifts the perspective away from the software layer, right?
It totally does.
Yeah.
I mean, for years now, the whole focus has been on parameter counts or, training algorithms, quantization techniques, all of that.
Visible stuff.
Right, exactly. But what this supercluster documentation reveals is that the primary bottleneck in AI right now, it's not really algorithmic anymore. It is strictly physical.
Meaning what exactly? Like materials?
Yeah, material science, fluid dynamics, and just massive, massive scale electrical engineering. I mean, the manual breaks down a system that integrates insanely high density compute with advanced closed-loop liquid cooling.
Wow.
And it has this autonomous management layer that operates in real time, basically just to prevent the catastrophic hardware failure we were just talking about.
Which brings us back to the melting chips.
Exactly.
Okay, so let's start at the absolute center of gravity here. The compute trays.
Yeah, the heart of the beast.
Right. These trays house the NVIDIA GB200 and the GB300 NVL72 architectures. Now, the documentation specifies a single rack integrating 36 NVIDIA Grace CPUs and 72 Blackwell GPUs.
Which is a huge shift.
Right, because a traditional server might pair 2 CPUs with, I don't know, maybe 4 or 8 GPUs.
Yeah, usually.
So seeing a 1:2 CPU to GPU ratio across an entire rack, that suggests something fundamental has changed in how the silicon is actually processing the workloads. It's like the CPU isn't the main engine anymore.
No, not at all. The CPU is basically just a data traffic cop now. It just feeds the tensor cores.
Okay.
And that ratio is highly deliberate.
Okay.
It actually addresses what engineers call the memory wall problem.
The memory wall. Break that down for us.
Sure. So historically, the GPU had to constantly pull the CPU over a PCIe bus to get its data.
Like reaching across a motherboard.
Right. And doing that introduces massive latency. It's just too slow. But the GB200 architecture uses a unified memory space. So the Grace CPU and the Blackwell GPU are connected via this ultra-high-speed die-to-die interconnect.
Meaning they're practically touching.
Basically, yeah.
Yeah.
They share the exact same physical memory map. So when you scale that up to 72 GPUs in a single rack, you aren't building 72 distinct computers anymore.
Okay, what are you building then?
You're constructing a single massive 72 GPU domain. The operating system literally sees one monolithic accelerator.
Wow. Okay, so it's not like a choir of 72 individual singers trying to harmonize. It's more like a single 72-headed hive mind entity that just processes a thought all at once.
That's a great way to put it, yeah.
Now, the manual details the memory specs for the GB300 variant specifically, and it says it has 288 gigabytes of HBM3E memory per GPU.
Which is a staggering amount of memory.
It is, and when you multiply that across the whole rack, the numbers just get absurd. But the choice of HBM3E over standard GDDR memory is critical here, right?
Oh, absolutely. It's essential for inference speeds.
Because HBM, high bandwidth memory, physically stacks the memory chips. Like it stacks the DRAM dies on top of each other, right?
Yeah, like a microscopic skyscraper. And then they punch these tiny microscopic holes called through-silicon vias, or TSVs, straight down through the whole stack.
Right, so you're physically shortening the tiny distance the electrical signals have to travel.
Exactly. And that physical proximity is exactly what allows the system to hit the performance metrics the manual claims, like the 10x higher tokens per second per user compared to the older Hopper generation.
Which means faster answers when you type a prompt.
Way faster.
Yeah.
Because, the distance data travels dictates both latency and power consumption.
Oh, right. pushing electricity further takes more energy.
Precisely. Pushing an electrical signal all the way across a motherboard trace takes orders of magnitude more energy than just dropping it a few micrometers down a TSV.
That makes total sense.
And that architectural density is what lets the NVL72 deliver like a 30x faster real-time inference rate for trillion parameter models and a 4x acceleration in training.
But wait, if they all act as one massive GPU, how do they physically talk to each other fast enough to not get completely confused? I mean, that introduces a secondary physics problem, right?
It absolutely does.
Yeah.
Because if all 72 GPUs are acting as a single logical unit, processing a massive mixture of experts model, all those intermediate calculations have to be shared among all 72 chicks instantaneously.
Right. If chip number 1 finishes its math and has to wait like 10 milliseconds to pass the data to chip number 72,
then your whole 30x performance gain is completely neutralized by network latency. You're just waiting around.
which means the internal network of the rack has to be as fast as the processors themselves.
Exactly.
Okay, so this is where the manual introduces the NVLink switch. The documentation states this switch enables configurations of up to 576 fully connected GPUs in and I love this phrase, a non-blocking compute fabric.
Yeah, non-blocking is the key term there.
Let's break that down, because non-blocking is doing a lot of heavy lifting. I mean, in a standard network topology, you usually have oversubscription, right?
Right, like a leaf-spine architecture.
Yeah, so if every single device tries to send data at maximum capacity at the exact same time, the central switches just don't have enough bandwidth. Data gets queued up, it gets blocked.
It's like a highway during rush hour.
Traffic jam. Exactly. So a non-blocking fabric means the highway is infinitely wide.
Basically, yeah. What's fascinating here is that the bisection bandwidth of the network actually equals the edge bandwidth. It guarantees that every single GPU can talk to any other GPU in the cluster at full speed, concurrently, with zero traffic jams.
Wow.
Yeah, and to achieve this, the manual lists the specs of the 4th generation NVLink and 3rd generation ND switch chips. They provide up to 1,800 gigabytes per second of all-to-all communication.
1,800 gigabytes per second inside a single rack.
Yeah. And each switch is housed in a 1U chassis, which is just 1.75 inches thick.
Just a little pizza box.
Right. But it delivers 25.6 terabits per second of full duplex bandwidth.
25.6 terabits. Okay, to put that in perspective for you listening, it's like downloading the entire internet in the blink of an eye, just happening inside a metal box that's less than 2 inches thick.
It's almost incomprehensible.
But wait, at 25.6 terabits per second, you are fundamentally pushing the physical limits of copper wire, right?
Oh, definitely.
Usually when we talk about data speeds approaching the terabit range, we're talking about optical transceivers and fiber optic cables. Light, not electricity.
Right. But converting an electrical signal coming out of the GPU into a photon, shooting it across a fiber, and converting it back to an electron takes power, massive amounts of power.
Oh, so there's an energy tax to using optics.
Exactly. So to avoid that energy tax, these racks rely on incredibly dense copper backplanes, or they use these specialized twin-ax cables routed over distances of just a few feet.
So the cables have to be incredibly short.
Yeah, the chassis size is physically constrained by how far an electrical signal can travel at that high of a frequency before the signal integrity just degrades into pure noise.
So the physical proximity is mandatory? You can't spread this out?
Nope. You have to pack it tight. And this unified, ultra-dense architecture allows the GB300 NVL72 to output up to 1.4 exaflop-TS of AI compute.
Exaflop-TS.
Yeah, 1 quintillion floating point operations every single second.
That is just... Oh, okay. But since you brought up the energy tax, we really have to talk about how this beast eats. Moving 25.6 terabits of data takes an astronomical amount of electricity.
Sure, you can't cheat the first law of thermodynamics.
Right. The electrical energy required to flip billions of transistors at those frequencies is staggering. And the manual breaks down the power delivery system, showing this massive shift away from individual server power supplies to what they call centralized 1U power shelves.
Which is honestly a brilliant engineering pivot.
It really is, because in a standard data center rack, you might have 20 individual servers, and each one has 2 built-in power supply units just for redundancy.
Right, so that's 40 separate power supplies taking up physical space.
Exactly. Generating their own heat, requiring 40 individual power cables plugged into a massive power distribution unit. It's a mess.
It is. So Supermicro just stripped all of that out of the compute trays. They moved the AC to DC conversion completely out of the server nodes and into these dedicated power shells.
And each shelf outputs a maximum of 33 kilowatts, right?
Yeah, 33 kilowatts. And the manual shows a typical rack integrating 4 of these shelves.
So meaning a single rack demands up to 132 kilowatts of continuous power.
Total, yeah. 132 kilowatts for one footprint.
To put that into perspective, it's like instead of putting tiny LEA batteries into 18 different RC cars, you just rip the battery compartments completely out, stack the cars on top of each other, and plug them directly into a miniature nuclear reactor.
That's a really good analogy that saves a ton of plastic and wires. And centralizing the power conversion gives you these huge efficiency gains.
How so?
Well, when you convert high voltage alternating current from the facility grid into the low voltage direct current that the GPUs need, you get conversion losses.
Right, nothing is 100% efficient.
Exactly. And those losses manifest as heat. By using these massive centralized rectifiers in the power shelves, you really optimize the efficiency curve.
And simplify the cabling, I imagine.
Oh, totally. Delivering 132 kilowatts using standard cables is basically impossible. The cables would have to be so thick you literally couldn't bend them.
Like solid logs of copper?
Pretty much.
Yeah.
And the impedance would cause unacceptable voltage drops anyway. So instead, systems like this use massive copper bus bars.
Bus bars.
Yeah, they run vertically down the entire back of the rack. The compute trays just slide in and plug directly into this highly electrified copper spine.
Okay, so you reclaim all that physical space inside the trays to pack the GPUs even closer together, which helps with the short copper network cables we talked about.
Exactly, it's all interconnected.
But 132 kilowatts of electrical energy entering the rack means 132 kilowatts of thermal energy must exit the rack.
Yep, every watt becomes heat.
And if you tried to cool 132 kilowatts of heat with traditional air conditioning and server fans, I mean, the sheer volume of air you would need to push through that 19-inch wide metal box would require jet engine velocities, right?
It would sound like a jet engine, and honestly, the friction of the air moving that fast would probably generate additional heat.
Right. So air cooling won't survive this. We have to move to liquid.
We do, because air has a terrible specific heat capacity. It's fundamentally an insulator, not a conductor.
So to remove that density of thermal energy, the medium must change. And this is where the manual dedicates a huge portion to the in-rack coolant distribution unit, or the CDU.
Yeah, the CDU is fascinating. The spec sheets detail SKUs capable of 100 kilowatt and even 250 kilowatt cooling capacities.
Inside the rack.
Inside the rack. The system uses these cold plates mounted directly, flush against the bare silicon dies of the CPUs, GPUs, and the NV switches.
Bare silicon.
Yeah. And liquid coolant is pumped through these micro-squeezed copper fins inside those plates, so it's absorbing the heat directly at the source.
Now, here's where it gets really interesting for the economics of a data center. The financial impact of this is buried a bit in the documentation, but it's massive. Liquid cooling actually reduces data center electricity costs by up to 40% compared to traditional air-cooled layouts.
Oh, easily. Because pumping a viscous fluid through a pipe is energetically far, far cheaper than spinning thousands of high RPM industrial fans.
Right. But I mean, injecting a pressurized fluid loop directly on top of 132 kilowatts of electrified bus bars and 72 irreplaceable Blackwell GPUs, that is an incredibly hostile environment.
It's inherently terrifying. Mixing massive power and rushing water, the engineering tolerances have to be absolute.
Right, because if a pipe bursts, you're looking at a multi-million-dollar sparkler.
Exactly, which is why the manual highlights the telemetry of the CDU to manage this environment. It's obsessive.
I saw that. This SuperCloud Composer software ingests all this real-time data. Coolant return temperatures, supply temperatures, facility water flow rates.
Valve ratios, pump RPMs. We literally see screenshots in the manual detailing pumps running at exactly 4,567 RPM.
Wow.
Yeah, and dissipating exactly 11.7 kilowatts of heat load at a specific millisecond.
But out of all those metrics, you were saying earlier that the most critical one tracked in that telemetry list is actually the dew point.
Yes. Dew point is the ultimate assassin in a liquid-cooled data center.
Okay, explain that for us. Because I just think of the morning grass being wet.
Well, it's the exact same principle. If the chilled water coming from the facility loop is too cold compared to the ambient temperature and the humidity of the server room, condensation literally forms on the outside of the tubes.
Oh, like a glass of ice water sweating on a hot summer day?
Exactly like that. But in this rack, a single drop of condensation falling from a sweating coolant tube onto that 54-volt DC bus bar.
Causes an instantaneous arc flash and a massive short circuit.
Yep, total disaster. So the CDU isn't just mindlessly pumping cold water. It actually has a dynamic mixing valve.
So it blends the water.
Yeah, it actively blends the hot return water that just came off the chips with the cold facility water. It ensures the fluid hitting the silicon is always just a few degrees above the room's dew point.
While still being cold enough to prevent the chips from throttling.
Exactly. It is a continuous high-wire balancing act of thermodynamics.
That is incredible. And it has to operate without interruption, right? You can't just turn off the cooling to fix it.
Never. The manual outlines the 1+1 redundancy of the CDU pumps for exactly that reason. They're fully hot swappable.
So paint a picture for us. Imagine being a technician.
Okay, so say a pump bearing begins to fail, and the telemetry registers anomalous RPM fluctuations. The secondary pump immediately spins up to handle the entire hydraulic load.
While the system is still running.
Yes, and a technician can literally walk up, physically unlatch the failing pump module that use these blind-made quick disconnect manifolds that prevent even a millimeter of fluid leakage. Yeah, they pull out this massive liquid pump from the rack and replace it, all while the system is still crunching exafloppy S of trillion-parameter AI models,
Right.
without dropping a single computation.
That seamless redundancy is just mind-blowing. But it makes me wonder, that's for planned maintenance or a slowly degrading pump. What happens when the physical infrastructure actually fails suddenly?
You mean a catastrophic breach?
Right. What happens if a microfracture develops in a manifold and coolant physically breaches the closed loop and starts spraying?
Yeah, the nightmare scenario.
Exactly. The manual actually provides the exact JSON code for the Redfish API for this. It's called the leak detection policy.
Which is fascinating because this code doesn't live in the main operating system of the server.
Right. It runs on the baseboard management controller, the BMC.
Right. And the BMC is a completely autonomous microcontroller. It has its own out-of-band network connection. It operates completely independently of the CPUs or GPUs.
Because its only job is hardware survival. So looking at this Redfish API mockup, the logic is pretty straightforward. It uses a policy condition logic set to any of.
Meaning if any one of its sensors trips, it takes action.
Right. It queries an array of physical sensors like leak detector cold plate or leak detector 1 manifold. And if a single drop of water bridges the electrical contacts on any of those sensors, the property string value registers as critical.
And what does the BMC do?
It bypasses the operating system entirely and executes a hard power off command, which makes perfect sense. Kill the 132 kilowatt power delivery instantly before the water short the bus bar and causes a literal fire.
Right. You want the power gone immediately.
But when you look closer at the JSON code, there's a parameter that initially seems completely irrational.
Oh, the delay.
Yes. It reads, reaction delay seconds, 120.
2 full minutes.
Right. If my server is currently spraying water onto electrified copper, why on earth is the system intentionally programmed to wait 2 full minutes before cutting the power? Why isn't it an instant shutoff? That feels like an eternity during a catastrophic leak.
It does feel crazy. But it actually comes down to the physics of fluid dynamics and the architecture of the silicon.
Okay, walk me through it.
Think about the water first. If you instantly sever power to a pump that is moving hundreds of liters of liquid at 4,500 RPM, the sudden halt of the impeller creates a massive pressure spike in the lines.
Oh, because the water has momentum.
Exactly. It's known as a fluid hammer effect. That pressure wave can violently rupture the intact hoses further down the line. You'd be turning a minor drip into an explosive flood inside the rack.
Oh, wow. You're slamming the brakes on a freight train of rushing water.
You really are. And then, on the electrical side, a sudden ungraceful power loss to 72 GPUs that are actively writing data to HBM3 memory. That will almost certainly cause massive data corruption.
Right, because they're in the middle of a thought.
Exactly. The PCIe lanes and the NVLink switches need at least a few seconds to flush their caches to non-volatile storage, so you have to let them finish saving.
So the 120-second delay is basically a highly calculated risk.
It is. It's the optimal window to gracefully spin down the massive pumps, relieve the hydraulic pressure slowly, and halt the inference workload without causing secondary physical damage to the hardware.
That is so wild. But wait, what if an admin decides they'd rather risk the data corruption than the fire?
Well, the documentation explicitly notes that this is a configurable policy.
Oh, so you can change it.
Yeah, an administrator can issue a PTCH command via the API to modify that delay. If a specific data center determines that their physical hardware risk outweighs the risk of data corruption or the fluid hammer, they can change the reaction delay seconds to ZO.
Instant shutoff.
Yep. And the BMC writes that configuration to flash memory, so it persists even across power cycles.
Okay, but orchestrating these API calls and monitoring the dew point across thousands of sensors and managing the firmware of the pumps, doing all that manually seems impossible. A human admin needs a way to actually monitor and control it from a safe distance.
Absolutely. You can't manage a deployment of this scale by writing raw JSON into a command line for every single rack. Enter the control room, SuperCloud Composer, or SEC.
SEC is amazing. It provides this highly structured hierarchy for the whole data center.
Right, it goes from POD, down to groups, down to the rack.
And then even down to the specific drawer level containing the CDU, the NVLink switches, and the specific compute trays.
It's like a zoom lens on a satellite. You can look at the entire POD, the whole fleet of racks, and then click down, down, down until you're looking at the exact RPM of left pump 1 in one specific drawer of one specific rack.
It really is. It allows an administrator to visualize the entire data center floor.
Yeah.
And the physical assets table gives you everything IP addresses like 172.25.230.3, and you can verify if a specific coolant distribution unit is running firmware version 0300 or 0700.
And it handles firmware updates too, right? Because updating firmware on a system like this seems incredibly risky.
Oh, firmware management on this scale is remarkably complex. I mean, the manual literally warns that flashing the firmware of the CDU triggers a reboot of the controller.
Wait, you're essentially turning off the brain of the cooling system while 132 kilowatts of heat are still being actively generated by the silicon.
Basically, yeah.
How does the system survive that reboot? Does the SCC temporarily halt the AI workloads to drop the power draw?
You'd think so, but usually the system relies on the thermal mass of the fluid loop itself.
The thermal mass, meaning just the sheer amount of water.
Exactly. Water retains heat incredibly well. Even if the controller reboots and the active dynamic mixing pauses for, say, 30 seconds, the massive volume of liquid currently circulating through the pipes acts as a thermal buffer.
Oh, so it just absorbs the heat temporarily.
Right. It buys you time until the BMC comes back online and resumes active pump control.
That is genuinely brilliant. But SCC is not just a hardware telemetry tool, is it?
No, not at all. And if we connect this to the bigger picture, the documentation heavily emphasizes its integration with the NVIDIA AI enterprise software stack.
Right, specifically NI microservices and the NeMo framework.
Yes. It's an end-to-end generative AI deployment tool. This represents the holy grail of data center operations, telemetry-aware workload scheduling.
Okay, telemetry-aware workload scheduling. Give me an example of what that looks like in practice.
Okay, so imagine you notice a rack is suddenly running hot. Maybe the facility water supply temperature rose by just 2 degrees.
Okay, a minor thermal spike.
Right. In the past, you just let the chips hit their thermal limit, and they would automatically throttle their clock speeds to cool down, which slows down your AI.
Which you don't want.
Exactly.
Sure.
A pure hardware dashboard would just flash a yellow warning light. But with full software integration, the orchestration layer, typically Kubernetes, recognizes the thermal strain on that specific physical rack.
Oh, and does it move the workload?
Exactly. It dynamically migrates the active inference workloads to a cooler rack on the completely opposite side of the data center.
Wow. So it seamlessly correlates the physical reality of the coolant return temperature directly with the software reality of the AI's tokens per second generation rate.
Yes. It bridges the gap between hardware and software.
Which perfectly encapsulates the core insight of this entire manual, really. The digital world is intrinsically bound by physical constraints.
It is entirely physical.
Right. When we talk about AI models scaling up, when we hypothesize about next-gen models requiring 10x, 100x, or 1,000x more compute, we're not just talking about writing better code or clever math.
No, we are talking about the physical limits of how much copper you can pack into a 1U chassis before the electromagnetic crosstalk destroys the signal.
Right. And we're talking about the sheer massive volume of chilled water required to absorb the thermal energy of megawatts of electricity.
The Supermicro SuperCluster documentation basically provides a snapshot of the bleeding edge of current engineering, but it also reveals the trajectory we are on.
Which is terrifyingly steep.
It is. The physical density is rapidly approaching the absolute boundaries of material science. I mean, as power requirements push past 132 kilowatts per rack and move toward 200 or even 300 kilowatts, the traditional data center architecture will be forced into radical redesigns.
So what does this all mean for you listening? Well, the next time you sit at a desk and type a prompt into a generative AI, consider the physical domino effect you just triggered halfway across the continent.
It's quite a chain reaction.
It is. Your simple text string caused a dynamic mixing valve to open a fraction of a millimeter wider. It caused a massive pump to ramp up its RPM to counter a sudden thermal spike.
It pulled a surge of 54-volt direct current across a solid copper busbar.
Exactly. Blasting data across a non-blocking optical fabric at terabits per second, just for a single prompt. But looking at the extreme, almost desperate lengths detailed in this manual just to cool a single rack, you really have to wonder, where does this end?
That is the big question.
Because as AI models continue to grow exponentially, what happens when we simply cannot push any more water or pump any more power into a single metal box on land?
We'll have to look elsewhere.
Right. Will we have to completely redesign data centers to be submerged in the freezing depths of the ocean just to keep them from melting? Or will the vacuum and ambient zero temperature of space become the only viable environment to house the next generation of artificial intelligence? Keep exploring, keep questioning, and we'll see you on the next deep dive.